Now, I know some of you have eyes that just glaze over when scientists start talking big words, and believe me, I've been to presentations where I sit there and I think, gosh, it feels like the goal of what you're doing right now is just to make me feel stupid. That's not what I'm about. I'm going to explain how telomeres and telomerase work in such plain English that I probably will get really nasty comments from scientists telling me that I've oversimplified it. But that's okay, I'll deal with them. For you, I just want to make this really simple. If you remember back to about high school science, you've got a cell and it starts replicating itself inside until you've got two lots of everything, and then that cell divides. Well, what they didn't tell you in high school is that you've also got on the end of your DNA in there a tail, a long tail. When you're born, it's really long. And as you can imagine, what I'm going to say now is as you get older, it gets shorter and shorter and shorter. So every time that cell divides, you lose a little piece of that tail. And basically it's kind of, and that tail is called your telomere. And the telomere is sort of taking the hit, because when you duplicate something and then make one thing into two things, you can't still have 100% of what you had. So instead of not having 100% of your actual DNA, because that would be disastrous, the tail, the telomere takes the hit, takes one for the team, and just gets a little shorter. So every time the cell divides, the tail gets shorter. Now, these telomeres used to just be called a tail. That was all they thought it did. Oh, you got a long tail, you got a short tail, whatever. Then scientists realized that actually the tail is the clock of aging. And when I mentioned before about the Hayflick Limit, or if you haven't heard of the Hayflick Limit, that's the number of times that your cells can divide before they can't divide anymore. And the Hayflick Limit is basically the count of that tail. And once it gets to, so you start off with 15,000 base pairs. When it gets to 5,000 base pairs, that cell can't divide any longer and it carks it. That cell dies. Out of there, gone. So basically, your telomere is on a path to dying. Sorry, it's dying from the second that you're born. But there is something, a gene inside that DNA called telomerase. So please don't let me confuse you. The tail is the telomere and the gene is called telomerase. So what telomerase does is when your cells divide and the telomere shortens, telomerase can switch on and express an enzyme also called telomerase, which makes that tail longer again. So you get a tug of war. So you're not just going, you get to go shorter, longer, shorter, longer. And if you can express enough telomerase, you can go longer than you actually were. That's where we get age reversal. Now, why is this just not happening anyway, you might ask? And there are creatures and microbes and beings on this earth that do express telomerase and show absolutely no sign of aging. We're talking about planarian worms, we're talking about clam shells, there are some whales, tortoises. They show no signs of aging. Just as an aside, they actually have the lowest incidences of cancer of any species that there is, because the longer your telomeres are, the less likely you are to develop cancer. But that's a total aside. You have telomerase switched on in some of your genes. In your reproductive cells, telomerase is switched on. Now, the reason for that is if I'm going to take an egg and take a sperm and put them together, that's two cells. And before that little bubba is born, we have to make two cells into 3 trillion cells. Now, remember what I said, cell division equals aging. So, yeah, a lot of aging goes on in the womb. So we're going to go from 2 cells to 3 trillion. If your reproductive cells did not express telomerase and therefore reverse that aging, so push, pull, you'd give birth to something older than yourself, which is a bit of a mind warp, really. So your reproductive cells, it's called your germline, and most animals with telomerase, this is how they protect themselves, with that germline. Otherwise, humans would have lasted like 2 generations, then we would have been out of here. So it's switched on in your reproductive cells. It's switched off in every other cell, but it's just sitting there, dormant. And it turns out there's actually a receptor blocking it. Now, the reason that it's blocked is up for debate. The one that I think has the most kind of votes behind it is for like evolutionary reasons. So for a race or a species to continue, you've got to get out with the old and in with the new. And, you know, way back when we were still evolving, we needed that. You know, we needed to breed and die. And it allowed the human race to evolve from cavemen to, you know, the Neanderthals to what we are today. But we're a kind of race now that likes to defy evolution, and we're using technology to do that. So we're like, hey, do you know what? We've got that gene in our cells. And for a lot of us, we feel like it's almost a mistake that it got switched off. And all we need to do is switch it on. So the molecules that we work with, they switch on your telomerase gene by simply putting something in there that attracts that block to open up. So we're opening the door slightly. So your cell divides, your telomere gets shorter, and we open that door slightly, and your telomerase gene expresses that enzyme telomerase, and your tail gets longer again. So essentially you're defying age. Now, I hope that was kind of an easy to understand. You could repeat it again, explanation of telomeres and telomerase and how they work.